Today we're going to present a brief overview of the ECOMP SDN Controller platform. The SDN Controller platform is based on the Open Daylight framework with ECOMP customizations. Starting in the upper left of this diagram, the three primary design time inputs to the SDN Controller platform are directed graph files, which are in an XML format, which define the behavior of the platform. And then there are two types of Yang models which can be fed into the platform. There's network data models, which represent the data which is stored internally within what's called the config tree or the operational tree. And we'll discuss that more in a moment. And also the service data model, which describes the API exposed by the platform. These models, primarily the XML, are fed into a service logic compiler, which in the case of directed graphs, compiles those into Java objects which are stored in a local MySQL database. In the case of Yang, these models are actually compiled by the Yang Tools compiler, which is part of the Open Daylight framework, which generates the code for the API handler. The primary interface, northbound interface at least, to the SDN controller is the Master Service Orchestrator, MSO, within the ECOMP platform. The Master Service Orchestrator uses a REST API to invoke APIs that are exposed by the API handler. As I mentioned a moment ago, the format of those APIs are defined in the form of Yang models. And when an API is invoked, the API handler essentially converts the inputs it receives into a format that can be consumed by the service logic interpreter and invokes the service logic interpreter, telling it to invoke the appropriate directed graph to implement the interface. The service logic interpreter then retrieves that directed graph from the MySQL database and proceeds to execute it, doing whatever it says to do. Besides the MSO, the other northbound interface of note is to a cloud platform orchestrator. And that interface is a slightly modified version of the standard OpenStack Neutron interface. Now, besides the northbound interfaces, we also have what is sometimes referred to as a sideways interface with ANAI, active and available inventory. The primary interface into and out of ANAI is REST. So the SDN controller will send REST puts and gets to ANAI to save and retrieve information from there. And there's also a dotted line interface that you see here, which represents notifications. ANAI and SDNC can notify one another of local data that might be of interest to the other side. On the bottom of the diagram here, you see a layer of network adapters. This layer is how the SDN controller communicates with various devices. And two examples that you see here in this diagram are a vCenter adapter, which could be used to talk to a vCenter to perform operations on VMware, or to a network device adapter. And some of the network devices that you might want to talk to might be various types of edge switches or interconnects and things of that nature. I mentioned earlier directed graphs. Directed graphs are the primary programming interface for the SDN controller platform. And the purpose of them is to extend the Open Daylight platform to allow rapid development and deployment of new network controller features. The service logic, meaning the business logic, is defined in a graphical format as directed graphs. The directed graphs are then compiled into Java objects which are stored in the SDN controller database. And the service logic interpreter is able to retrieve these Java objects and execute them within the Open Daylight platform. If new primitives are needed, they can be added to the platform for consumption by directed graphs in the form of OSGI bundles. The SDN controller was designed to be highly modular, most of the functionality being exposed as OSGI services. And those OSGI services can be accessed as nodes within the directed graph. Now, most of those modules fall into one of the following categories. API handlers, which expose northbound interfaces defined as Yang models, device adapters, which are used by what are called configure nodes in the directed graph to update devices, resource adapters, which are used by resource management nodes, like get resource to access resources, such as local MySQL tables, and then finally Java plugins, which are invoked by the execute node. This slide shows you the current node types supported by the directed graph language, and they fall into 5 major groupings. There's your standard flow control primitives, like a block, which is just like a block in any conventional language, call, which allows you to call another directed graph. Think of it as a standard subroutine call, a for loop, return node, a set that allows you to set variables, and a switch node that allows you to make decisions. Then there's a device management, which is the configure node, Java plugin support, which is the execute node, logging and recording, which is the record node, and then finally resource management. And there are a number of nodes here. Delete exists, get resource is available, notify, release, reserve, and save. Basically, these are your standard CRUD capabilities. Create, read, update, delete. On this slide, we see an example of a fairly simple directed graph. This one happens to include a call to a Java plugin. So down here is the main body of the graph, and as you can see, it starts with a block, which is a block like any other language. It just means execute all of its subnodes. The first node is a decision node. It looks at the length of a string. If the string length is greater than 1, it doesn't need to be left padded. If it is not, then it does need to be left padded with a 0, which is what you see in these two set nodes. Then there's an execute node to calculate something called a GRUA. It doesn't really matter what it is, except that it's something fairly complicated that you really would not want to do in the directed graph language. And that's an example of why you would use a Java method, so that you can do something that's computationally intense without having to write all kinds of complicated directed graph language. And then in this example, the next things it does is it assigns the city and state part. It does a couple of sets. Sets the city and state part of the host name. It then saves the names it just calculated and updates the config tree. So the reason why one would do directed graphs as opposed to writing things directly in Java is that with directed graphs, you don't have to do the standard Java compile, deploy, and restart cycle. You can make changes in real time without having to restart the controller. We had a recent example on one of our projects where we needed to be able to handle a situation that had not been anticipated when the requirements were written. We had a case where one of our sites had multiple subnets for O&M addresses, which had not been anticipated when the project was first initiated. We were able to solve that problem by a change to a directed graph, which we were able to deploy without a need to restart the container, which allowed us to turn that fix around much, much faster than if we had had to do it in Java.